Hello students, welcome to EPG Pathshala. I am Dr. Varun Vyas from Department of Physics and Astrophysics, University of Delhi. Today we are going to talk on module Auger Electron Spectroscopy, Principles and Instrumentation under the paper Characterization of Materials. After completing this module, a student will be able to understand instrumentation, kinetic energies of electrons, and electron optical columns associated with this spectroscopy technique. Auger electron spectroscopy, that is AES, is a non-destructive electron spectroscopy technique for partial identification of elemental composition of materials. Samples can include surface, thin film, interface, etc. High surface sensitivity, that is analysis depth less than 100 Armstrong, and a relatively low detection limit, that is around 0.1 atomic percent, makes AES a very popular technique for surface analysis. Auger spectroscopy can also be used to differentiate between elements which may be adjacent in periodic table. Additionally, it can be used for almost all elements, that is from lithium to uranium and beyond. AES also demonstrates atomic number dependent sensitivity, which may vary by up to one order of magnitude. Bonding or chemical state information can be obtained from chemical shift and the line shape observed in AES. However, Auger spectroscopy is less accurate than XPS for obtaining bond information. AES has depth resolution of 5 to 25 angstrom, which makes it particularly attractive for depth profiling and simultaneous ion sputtering. The lateral resolution of Auger spectroscopy is less than 100 angstrom and is much better than XPS. Thus, the nanostructures can be readily imaged along with creating a 2D map of elemental composition of surface via scanning Auger spectroscopy, that is SAM. SAM. AES is a rather fast technique. Despite being an expensive and sophisticated technique, Auger is a 3-electron process, wherein an electron beam that is having 1 to 10 electron volt energy is bombarded onto a solid surface. Impact of the beam ejects an electron from inner or core shell of surface atoms, thereby creating an ionized excited atom. An electron from an outer shell can occupy the vacancy produced in the core shell via a non-radiative transition. The excess energy of electron is removed via 1. X-ray emission. This phenomena forms the basis of X-ray fluorescence, that is XRF, and electron probe EMP analysis. Second, emitting another electron from the atom. These atoms are termed as Auger electrons after Pierre Auger, discovered discoverer of this process in 1920s. Around the same time, Liz Metna also invented this effect in an independent investigation. The X-ray emission of X-rays creates singly ionized atoms, whereas the atoms in Auger process becomes doubly ionized. Interestingly, AES cannot be used to detect hydrogen and helium, as Auger involves 3 electrons. Further, even though lithium possesses 3 electrons, an individual lithium atom in its ground state does not produce Auger peaks. because the atom has only two energy levels, which have electrons. Nonetheless, multiply excited lithium atoms have demonstrated Auger peaks. Additionally, electrons present in the valence band of solid lithium facilitate Auger transitions of type KVV, short mean free path, which is responsible for the high surface sensitivity of this technique. Even though atomic excitation can occur up to the depths of around 10,000 angstrom beneath the surface, it is only from the depth of approximately 100 angstrom that Auger electrons can be emitted without losing energy. On the contrary, electron probe analysis, that is EMA, wherein X-ray photons are detected in rather a bulk technique shown in figure 1. Electronic states related to Auger process have very short lifetimes. Thus, according to Heisenberg's uncertainty principle, the peaks in the spectrum are usually wide, that is between 1 to 2 electron volt. Auger electrons' kinetic energy is specific to the emitting atoms. Consequently, particular elements can be identified by measuring these kinetic energies of the emitted electrons in the Auger process. Since the kinetic energy of electrons in the Auger process is determined by binding energy, that is Be, of the electronic levels, any shift in the kinetic energy yields detail about oxidation state and the bonding environment of atoms present at the surface. Additionally, quantitative details can be obtained from the Auger peak intensities. The number of electrons detected is plotted against the kinetic energy of electrons to obtain direct Auger spectrum. In addition to this, for distinguishing small peaks in spectrum, usually first derivative of number of electrons is plotted against the kinetic energy. Derivative Auger spectrum serves two purposes. Auger peaks are enhanced, and the background produced from the secondary backscattering electrons is suppressed. Ultra high vacuum chamber is required for AES investigations, such that the electron beam can travel freely and contamination from the atmosphere is avoided. Principle: Figure 2 depicts the schematic of Auger phenomena in solids. The figure shows K L2 L3 Auger transitions, which involve ionization, relaxation, and emission, and is summarized below. A. Ionization: high energetic incident beam electrons remove an electron from the core shell of an atom, leading to the formation of a vacancy in K shell. Thus, an electronically excited ion is produced. B. Relaxation: the K shell vacancy created during the previous step is quickly filled by an electron coming from L2 shell via non-radiative transition. C. Electron is emitted from L3 shell, thereby releasing the extra energy of the excited ion. Auger transitions are named on the basis of the energy level involved in the process. Example: the transitions involved in the above figure is named K L2 L3. In certain cases, such as atoms having high atomic number, many Auger transitions are available. However, most of them have low probability of occurring. Further, some of the energetically allowed transitions are also forbidden by the selection rules. If a valence electron takes part in other transitions, letter V is used, such as KLV, KVV, etc. Transitions involving core electrons use letter C, such as CVV. Transitions of ABB, such as KLL, LMM type, are strongest. Another strong transitions are ABB type, also called as Coster chronic transitions. Emission of X-rays is a competing phenomena for Auger process, since the energy difference between the core and the outer levels can equally be realized in form of characteristics X-ray. Therefore, the sum of the yields of the Auger emission and X-ray emission is 1. AES typically operates in the energy range where the probabilities of Auger emission are much higher than that for X-ray emission. In addition to this, the cross-section for Auger transitions in elements having low atomic numbers is much higher. Includes the measuring of kinetic energy of Auger electrons, which are characteristic to the elements of the sample. Uncertainties of up 1 to 2 electron volt are tolerable in measurement of kinetic energy for elemental identification. However, analyzing the Auger chemical shift, this uncertainty in kinetic energy should not exceed 0.1 to 0.2 electron volt. Nowadays, the databases are available which can be compared with the obtained results. However, earlier AES relied on the measuring of kinetic energy of electrons. The steps involved can be summarized as follows. Approximations are to be made in order to determine kinetic energy of Auger electrons. Suppose in a hypothetical ABC type Auger transition, a vacancy is created in A level by removing an electron from it. This vacancy gets filled by an electron from B level. An Auger electron is emitted from C level. Let Be of the electrons in neutral atom for A, B, and C level are Ea, Eb, and Ec respectively. When electrons from the B occupies the vacancy in A level, an energy, that is Ea minus Eb, is transferred to the third C level electron, which is Auger electron. Thus, the kinetic energy EABC of Auger electrons can be expressed as EABC, which is equivalent to Ea minus Eb minus Ec. This is represented as equation 1, corresponding to its unique set of energy levels. For instance, the energy for K, L1, L3 Auger transitions in aluminium can be calculated as E K L1 L3 is equivalent to Ek minus El1 minus El3. This is written as 1560 minus 118 minus 73, and the net energy, this equation we get, is 1369 electron volt. We altered to include work function of spectrometer because Auger energies are usually referenced to the Fermi level. If good electrical contact exists between the sample and the sample holder, then Fermi levels of the sample and instrument are equals. Therefore, kinetic energy of ABC Auger electrons is approximately given as EABC, that is equivalent to Ea minus Eb minus Ec minus phi a. This is represented as equation 2. Here, phi a represents the work function of the spectrophotometer, and its typical value is 4 electron volt. EABC comes out to be 1365 electron volt as the energy of KL1 L3 Auger transition in aluminium. This reduces the disparity in measured and calculated values of 11 electron volt. For neutral atom, equation 1 can be further filtered by considering the change in the binding energy of a level accompanying ion formation. Here, EABC is equivalent to EA minus EB minus E star C minus 5A. This is represented as equation 3. Here, E star C represents the binding energy of a level in presence of a core hole. Equation 3 can be employed to determine energy of Auger electrons based on various empirical approximations. Instrumentation. Surface sensitivity in AES technique e- evolves from the fact that in solid materials, emitted electrons generally possess energies in the range of 50 electron volt to 3 kilo electron volt and have relatively shorter mean free path. Therefore, escape depth of electron is limited to few nanometer in the target surface, which gives AES a higher surface sensitivity due to lower energy of ultra electrons. Typically, AES runs under the condition of ultra high vacuum. This prevents electron scattering from residual gas atoms and development of thin gas adsorbate layer on the sample surface, which results in degradation of analytical performance. A standard AES setup, that is figure 3, involves the following component: A electron source and electron optical column forming an electron probe on the sample surface; B ion optical column to clean the surface and sputtering of for depth profiling; C electron energy analyzer; D a secondary electron detector and a pulse counter; E computer controlled and display systems. Modules A to D are located inside an ultra high vacuum chamber. Electron optical column. An optical column focuses electron beam from an electron source to the sample surface. The electron beam must be monoenergetic, of small size, and highly bright. Electron radiating the sample have energy in 2 to 10 electron volt range with a beam current of 10 raised to power minus 8 to 10 raised to power minus 5 ampere. Auger scanning microscopy uses energy up to 35 electron volt and current 10 raised to power minus 9 ampere to create a beam of approximately 100 angstrom in diameter. Electron source must have prolonged life and higher temporal stability. Four major types of electron sources are: 1. Tungsten thermionic emitter with approximately 2700 Kelvin operation temperature. They produce low electron density, owing to low brightness and large beam size. They are preferred for AES analysis where high resolutions are required. Second, the lanthanum hexaboride LAB6 thermionic emitter with operating temperature of approximately 1850 Kelvin and lower work function than tungsten can provide high laser resolution since they generate high temperature in presence of high electrostatic field and creates high brightness. However, this emitter becomes unstable on encountering a residual gases, thus ultra-low pressure, that is 10 raised to minus 10 torr, are needed. 4. Hot field or zirconium oxide or tungsten Schottky type field emitter operable at approximately 1800 Kelvin. This type of emitter can produce high current density. The ions thus produced are accelerated into a focusing lens column. Typically, inert gases, for example argon and xenon, are used with the hot tungsten filament. C. Electron energy analyzers. The number of electrons emitted N are measured as a function of their energy E by using electron energy analyzers. Most widely employed analyzers are 1. RFA or retarding field analyzer, second CMA or the cylindrical mirror analyzers, third CHA or concentric hemispherical analyzers. Retarding field analyzers suffer from inadequate energy resolution and poor signal to noise ratios due to the average transmission efficiency. Thus, RFA is generally employed in low energy electron diffraction investigations and not preferred for AES. CMA has a high transmission efficiencies, compact size, and is simple to use, making them suitable for Auger spectroscopy. CHA is used for Auger spectroscopy whenever a chemical state analysis is performed, since they have higher resolution. CHAs include an input lens and hemispherical analyzer and are commonplace in XPS energy analyzers. CMA and CHA are band pass filters (BPF), while RFA is high pass filter. The BPF allows passage of electrons within within a band of energy at pass energy, leading to the energy resolution of E by E. As the as RFA detects electron having energy greater than the specific energy E, the spectrum is differentiated once to determine N as a function of E spectrum. Comprises several small channel trons joined together to create a disk. Electron intensity is measured via pulse counting. Computer and display systems. Sophisticated computer control, data processing, and display systems are common to all modern AES instruments. The function of computer control system are: first, setting up conditions for analysis; second, efficient collection and storage of data; third, data processing; and finally, fourth, displaying results in form of a spectra. In this experimental configuration shown in figure 3, first the focused electrons get incident on a solid sample, and then the emitted electrons get deflected towards a cylindrical mirror analyzer. In detector, Auger electrons get multiplied and the signal is advanced for a data processing. Finally, the accumulated Auger electrons are recorded as a function of energy against broad secondary electron background spectrum. Because the Auger peaks have small intensities relative to the background noise, AES is generally operated in a derivative mode that highlights Auger peaks by modulating electron collection current by applying small AC voltage. Using setup shown in figure 3 by detecting the signal at frequency omega and plotting 1 can get the Auger fine structure. In this Auger structure, one can clearly see the little secondary peaks neighboring the main Auger peak. The secondary peaks arise because an element may be present on the surface in different chemical states. So students, let us now summarize what we have learned in this module. In this module, we studied about Auger electron spectroscopy, which is a non-destructive electron spectroscopy technique used for partial identification of elemental composition of materials. We learned about how this technique has much better lateral resolution as compared to XPS. Under instrumentation, we learned about electron gun, optional ion source, etc. associated with spectroscopy setup. Thank you.